Hello, this is ME490 Sustainable Energy Applications. I'm back with another energy balance term, WSEP, or separation work. My name is Abdallah Ghazali and I'll be the narrator of this presentation. For the agenda, I'll provide some background information, then talk about the methodology on how to calculate that WSEP term. It's generally going to be a simple equation that we're plotting versus temperature. And finally, I'll share my results. For the background, we need to understand the big picture. So we're trying to get hydrogen or carbon monoxide and combine them to form synthesis gas. However, that hydrogen or carbon monoxide do not exist independently. They're always lumped in some other big products. So carbon monoxide is mainly lumped in carbon dioxide and hydrogen is mainly lumped in water. We're going to assume that A plus B is that big lumped product and it's coming into a separator. We're going to supply WSEP or separation work to get it separated into pure A and pure B. In case of water, it's pure hydrogen and pure oxygen. In case of carbon dioxide, it's pure carbon monoxide and pure oxygen. Next, we're going to talk about the WSEP term. So WSEP Rev is the separation work assuming that there's no irreversibilities. It's negative RU times T reaction times YA natural log YA plus YB natural log YB. This whole quantity is in units of kilojoules per mole, where RU is the universal gas constant, 8.312 kilojoules per kilomole Kelvin. T reaction is the temperature at which the separation is taking place, and it's in units of Kelvin. YA is the mole fraction of the fuel, so mole fraction of either hydrogen or carbon monoxide, and YB is the mole fraction of oxygen plus whatever left over from the initial product, so either water or carbon dioxide depending on the reaction. So now that we know this term, we already said that we assumed that there's no irreversibilities. This is an ideal case. We don't live with ideal cases, so we need to account for irreversibilities. This is going to give us actual work, WSEP actual. Luckily, they're related by this term, eta 2. So eta 2 is the second law efficiency, or the separation efficiency. It's the WSEP rev term over the WSEP actual term. So in order to get the WSEP actual, we just need to divide WSEP rev over eta 2. So here we have it. WSEP actual is WSEP rev divided by eta 2. This is going to be the final equation that we're going to be using, and we're going to be plotting this actual separation term work versus temperature in the next slide. I want to talk briefly about this. So we said already that we're getting pure A and pure B outside. However, this is not always the case, as mixing can sometimes happen, and when mixing happens, we lose some work due to that, so we can adjust the equation to account for that mixing by just subtracting mixing due to work from the equation, and we get the separation work accounting for mixing, but still assuming that there is no irreversibilities. So if we're assuming that there is irreversibilities, we just again divide by the efficiency term and we get this final equation. So this is going to be accounting for mixing and assuming or accounting for irreversibilities. However, this is just a side. So for the results, we need to understand the relationship between mole fractions versus temperature. So I plotted the mole fraction of the reaction species versus temperature, and clearly there is a relationship between the two. So the initial product decreases significantly versus temperature on the other side, and at the same time the mole fractions of the products increase significantly with temperature, with the mole fraction of oxygen being always half of the mole fraction of the fuel, mainly because of that 2-to-1 relationship in the chemical equation. So now that we know that there is a relationship between mole fractions and temperature, we can say that WSEP actual depends not just on this term, but also on this YA and YB if we're to plot it against temperature, since we already said that they also depend on temperature, so they're going to have an impact on WSEP actual. But in order to make things a little bit simpler, we are going to assume 10% mole fraction of the fuel, and this dictates 90% of the other stuff. So this means we're fixing YA to a value of 0.1, 10%, and fixing YB to a value of 0.9 or 90%. So this means we're treating this whole thing as a constant, and RU is already a constant, and eta2 is already constant. So if we were to plot WSEP actual against temperature, we see that since everything is a constant, that this is going to be a linear pattern. So indeed, that's true. It's a linear pattern. This graph shows the separation work actual versus temperature for 3 different efficiencies, 10%, 20%, and 30%. Clearly, as the efficiency goes up, we're expected to lose work or not lose work to get lower work, because we're dividing by a higher number, which leads to a lower overall number. So if we pick 3000 as a temperature, a 30% efficiency separator is going to have lower work compared to a 10% efficient separator at a given temperature, say at 3000, as you can see here.